All right, in our previous video, we looked at approximation methods to estimate the area up underneath the curve. And so today, in this video, what we're going to do is we're going to tie in our approximation method into the definition of what a definite integral is. And in order to do this, I'm going to use Desmos. And so I'm going to open up Desmos here, and we're looking at this graph of some wave or some curve, and we're going to look at this curve, and we're going to go from 1 to 4. And if we wanted to find the area or estimate the area up underneath the curve, what we talked about in our previous video was estimation using left endpoint rectangles, or we used right endpoint rectangles. We looked at midpoints, and we also looked at a trapezoidal approximation method. Now, regardless of the approximation method we use, let's say I have right endpoint approximation method here, and I got 4 rectangles showing. Notice what happens as we start to increase the number of rectangles to approximate this area up underneath the curve. As I start adding more and more rectangles or increase the number of subintervals, notice how the gap in between the curve and the spacing or the areas of the rectangles is getting smaller and smaller and smaller. In fact, we start to get a closer and closer fit to the curve. Now, we're still off because we're approximating, but the estimation gets closer and closer and closer. So you see the effect of increasing the number of rectangles versus having a smaller number of rectangles, regardless of the approximation method. So if I switch to midpoint and I started increasing it, you notice how the spacing is a little bit tighter and better as I increase the number of rectangles or subintervals. Now, you can really see it with the trapezoid, because the trapezoid sums have they're the most accurate approximation method we have. So if I start with 4 trapezoids and start to increase that, and I'm going to increase it towards 20, notice how it's becoming a better and better and better fit, where we can almost get the true area underneath the curve. Now, to generalize what we did, basically we are increasing the number of geometric shapes that we're using to add the areas together to better our approximation of this area under the curve. So let me go back to our working towards our definition of this definite integral. And so to simplify our process, let's say we're just looking at the area of a rectangle to approximate the area up underneath the curve. Well, the area under the curve is going to be the sum of however many rectangles I'm going to use of the width of the rectangle, which is the change in the x, times the height of the curve or the height of the rectangle for that particular x value. This is called a Riemann sum for the interval from A to B. And the accuracy depends on the number of rectangles that we have. The width of our subinterval, note if I generalize this process, is basically you take from start to finish. So if I'm going from x is a to x is b, I'd go b minus a divided by the number of subintervals I wanted to use. So that's what change in x is representing. The c of k here, that's basically just the corner in terms of our rectangle. So how would we write an equation based on the corners? If I'm looking back at my diagram, I'm looking at my right endpoints here that are determining the function's value. So this c of k would just be some expression where I would plug in for k, according to sigma here, to determine what the x value is that I would plug in to get my corresponding height or y value of the function. So let's continue on. Well, as I increase the number of rectangles towards infinity, we are getting a better and better approximation of that curve, and we saw that with Desmos. And there's an alternate notation here that I have on the left-hand side, which uses this notation, which represents the width of the the width of the largest subinterval. So as we increase the number of rectangles or the number of subintervals to infinity, what is happening is the largest subinterval is going to be approaching a size of 0. Sometimes you'll see this limit notation written, but this limit on the left is the same thing as the limit on the right-hand side, but the right-handed one, which is the limit as n approaches infinity, is the most common one that you'll see, and that's the one that we're going to use. So the limit as n approaches infinity, so as I increase the number of rectangles I'm using for my approximation, that approximation as n approaches infinity is equal to the definite integral from a to b of f of x dx. Now, f of x is basically the same thing that we have right here. Dx is my change in x, or differential in x, is basically the same thing that I have right here. And so we kind of see how they tie in together. So what I want to do is I basically, here to start with, is I just want to take and I want to write definite integrals as their Riemann sum, as the limit of a Riemann sum, or look at the limit of a Riemann sum and then write as a definite integral. Okay, we're looking here at this first problem where we have the definite integral from pi to 2 pi of cosine of x dx. Now, we're not trying to evaluate it. We're trying to write it as a limit of a Riemann sum. Well, the limit that we're using for a Riemann sum is basically saying that a definite integral from a to b of f of x dx is equal to the limit as n approaches infinity of the summation, and I'm going to use I, so from I is equal to 1 to n, I just stands for subinterval, of f of ci times change in x. What I need to do is I need to start finding these pieces that what we have here. Well, change in x is the width of my subintervals. The width of my subinterval, change in x, is going to be equal to b minus a over n, the n representing the number of subintervals I'm using. Well, for a definite integral, a is the lower limit, b is the upper limit, and so we can get the change in x to be 2 pi minus pi over n, which is equal basically to just pi over n. So I know that the change of x is equal to pi over n. Now, looking at our problem, the function that we have, f, so f of x, is just going to be cosine of x right here. The last thing that we would need to determine is how we would write an expression that represents our corners that we would use for our rectangle approximation, ci. Well, it's easiest to do this if I start writing out some subintervals. So if I start writing out the subintervals for my approximation, I'd start with a, and I'd go with pi, and then plus the endpoint of that, not plus, the right endpoint of this interval would be pi plus the width of the interval. Well, the width of the interval will be pi over whatever n is. So that would be my first subinterval. My second subinterval would go from pi plus pi over n to pi plus, and then the endpoint of my second interval would be pi over n times 2, because I would have to add whatever pi over n is 2 times the pi to get to this second endpoint. And this would continue on until eventually I got to 2 pi. Our corner that we're using, ci, it's easiest to write an equation for the right endpoints, and that's what we're going to use. So an expression that would represent all of the right endpoints of these subintervals would be pi plus pi over n times whatever subinterval we're in, called I, where I is 1 in my first subinterval, I is 2 in my second subinterval, and then so forth. So we're going to put all of this in together to write our limit. So that definite integral is going to equal the limit as n approaches infinity of the summation from I is equal to 1 to n of f is cosine. Inside of the cosine, we're putting our corner expression, so it'd be pi plus pi over ni, and then we have our times our change in x, which we'd have times pi over n right here. So that limit is equal to that definite integral that we were given. Okay, so new problem here. We have the definite integral from 0 to 3 of e to the x dx, and we want to write the limit of the Riemann sum. Well, let's start identifying parts. So we know that f is going to be e to the x. All right, that part was easy. Now, let's go find delta x. Well, delta x is the width of my subintervals, which you would take the overall span, so from 0 to 3, so I'd go 3 minus 0, and divide by the number of subintervals I'm going to use, which would be n. So my change in x would be 3 over n. So we got that part. Now we want to write an expression for c, our corners. Well, to do that, let's write out our first couple of subintervals we'd start with 0. The right endpoint would be 0 plus 3 over n. And then the second subinterval would start at 3 over n, and then it would go to 3 over n times 2, which would be 6 over n. And then we would continue on, and then eventually we would get to 3. Well, writing our corners, it's going to be easiest to use the right endpoints. And so our right endpoints are basically going to be 3 over n times whatever interval we're in, first, second, third, so forth. So we'll say 3 over n times I. Now we're ready to write our limit. That definite integral, the limit of the Riemann sum, which would be the limit as n approaches infinity, of the summation from I is equal to 1 to n. Now, f of x is e to the x, so I'd write e to the, and now instead of x, I'm going to put my corner, so it'd be e to the 3 over ni. And then we have times our change in x, which would be 3 over n. Okay, now we want to go the other direction. And we want to write the definite integral from the limit of the Riemann sum. And so recall what our limit represents. So this represents the definite integral from a to b of some function of x dx. Let's start with what's the easier parts to find. Well, f in this case, f of x is equal to the ln of x. Now, we could also look and we could figure out what delta x is, which is going to be 5 over n. So we know that delta x is equal to 5 over n, but recall that delta x before is b minus a over n. So that represents the overall distance that we have from start to finish. So I'm going to have a unit, it's going to be 5 units difference from a to b when I'm writing my bounds here. So right now, all that we know is that this represents the definite integral of the ln of x times dx. I have to figure out what a and b are. Well, to do that, we're going to use our corner expression, which is what is on the inside of the natural log function, 2 plus 5i over n. And looking at this notation, because of the I that we have, is we are looking at the right endpoints, which is telling me that the 2 represents the starting amount. So that 2 is A. And B, so if I know that A is 2, I have 5 over n is equal to B minus 2 over n, which means that B has to be 7. So there is the definite integral represented by that limit. Okay, one more here. We want to write what this limit represents in terms of a definite integral. And so we'd start by trying to figure out what f of x is. What is f? Well, f is going to be the square root function, so we'll call it the square root of x. So my definite integral, my f of x is going to be the square root of x, and then we always have dx on the end. Now we need to figure out what our bounds are. Well, we look here, we have 3 over n. 3 over n is my change in x. So if my change in x is equal to 3 over n, that means b minus a over n has to equal 3 over n. So the overall space from a to b is going to be 3. Well, to figure out what a is, I need to determine my corner expression, which is what's on the inside here. So 4 plus 3i over n. And the 3i over n part is basically using my spacing, which is telling me that 4 is my lower limit of integration. It's going to go there on the bottom. So now that I know that that's 4, the space in between start to finish was 3, so the upper limit is 7. Here is my definite integral represented by that limit. Okay, so we made a connection between the definite integral and the sum of the individual areas of rectangles or trapezoids up underneath the curve that that function is representing. So what we're going to do is we're going to define the area under the curve from A to B as an integral from A to B. Now, there's something to keep in mind here is as long as the curve is non-negative and integrable, which we'll learn more about that later, then the area up underneath the curve is going to be the same thing as what the definite integral is. I'm kind of leading to something that I'm not ready to talk about until we get a little bit further along. So let's look at this definite integral here. The definite integral from 2 to 9 of 3 dx. Well, we want to use a geometric approach right now until we learn some other techniques to determine the area up underneath the curve. So if I create the graph of this function, this is basically just the horizontal line, y equals 3, and we're going to look from 2 to 9. And so that definite integral is going to equal the area up underneath that curve from 2 to 9, where if you look, you basically have a rectangle, which that rectangle is going to have an area of base times height. Well, the base of that is 7 and the height of that is 3. And so the area there is going to be 21, which is what that definite integral is going to be. Okay, so let's look at this next one here. We have the definite integral of the absolute value of x dx going from -2 to 1. And we want to use a geometric approach to figure out what that definite integral is going to be. So what we're going to do is we're going to find the area, basically, of those two triangles, and we're going to add them together. Well, this first one, the area would be 1/2 base times height, and that's going to give me 2. And then I'm going to add that to the area of the second one, which would be 1/2 times 1 times 1, which is going to give me 1/2. And if I add those together, I get 2.5. So far, it's the sum of the areas that we have. All right, let's look at another one. We want to go from -3 to 3 of the square root of 9 minus x squared. That equation right there is the top half of a semicircle. We have to be able to recognize that, where the radius of my semicircle is going to be the square root of that number. And so this definite integral is going to equal the area up underneath that curve, which is simply going to be pi r squared divided by 2, and which we're going to get 9 pi over 2. Okay, and that brings us to our next part, which is what happens if the area of this curve is actually beneath the x-axis. And so we're going to look at the graph of f of x is equal to 3 minus x, and we're going to focus on the space between 4 and 8. And so graphically, if I look at that function, we want to go between 4 and 8. I'm basically trying to find the area between the x-axis and this curve, which forms this shape here. Now, the shape formed that we have is actually a trapezoid, and so the area that we have would be h over 2 times b1 plus base 2. And so we use our trapezoid formula, h over 2 times base 1 plus base 2, and so h is 4. So we got 4 over 2 times base 1 is 1 unit, base 2, it turns out to be 5 units, and so we get an area of this trapezoid to be 6 times 2 is 12. So the area of that shape is 12. Now, the value of the definite integral here is actually not 12, it's -12. And the reason why it's negative is because that region lies below the x-axis. So what we're going to do is we're going to improve our definition of a definite integral and say the definite integral from a to b is going to equal the signed area between the curve and the x-axis. Okay, so we're moving on to our next part here. We want to use what we know about the sine function and evaluate the following. And I'm giving you the fact that the definite integral from 0 to pi for sine of x is going to equal 2. Now remember that definite integral is equal to the signed area up underneath the curve. So between 0 and pi, that area right there for that region is equal to 2. So let's look at this next integral we have here. Well, what would the value of the definite integral be from pi to 2 pi for sine of x? So this region right over here, that what we'd have. Well, the region that we're looking at from 0 to pi is the exact same as it is from pi to 2 pi. The only difference is it lies beneath the x-axis, which means that that area, or excuse me, that value, the signed area, would be -2. Our next one here, we want to go from 0 to 2 pi for sine of x. Well, if I want to go from 0 to 2 pi, I would take the area from 0 to pi, which is 2, and add that to the area value that we have to go from pi to 2 pi, and 2 plus -2 gives me 0, so that definite integral would be 0. The next one here, we want to go from 0 to pi over 2. Well, pi over 2 lies halfway in between 0 and pi, which means that both of those sides there would be 1, and that graph is symmetric. That one portion here, it splits it right in half. So we could divide that region into 2, so it'd be 1/2 times 2, which means that that value would be 1. And so now we have a little bit of a tricky one here. Let's go from 0 to pi for 2 plus sine of x dx. Well, we know what 0 to pi is for sine, but the 2 kind of throws us a little bit of a curveball. Well, remember how we do this is basically I need to create a new graph for the function that we are looking at. All right, so I create a new graph for what it is we're looking at, but I only go from 0 to pi. Basically, all we did was we had to move this graph that we're looking at right here up 2 units. That's the effect that that has. So if I move it up 2 units, basically my answer here, because we're looking at signed areas, is going to be the area of this top part, which it was given to us that that area is 2, plus whatever the area is of this bottom piece. Well, this just makes a rectangle, and that area is going to be the height of the rectangle times the base of the rectangle, which is 2 times pi. And so we could say that this is going to equal 2 plus 2 pi. Now, for right now, if we encounter a definite integral, we're going to use our calculator to evaluate some of these until we learn some integrating methods. And depending on your calculator you have, there's a couple of steps that you could use to evaluate. Now, an important thing to note is that if you have trig functions, we need to have our calculator should always be in radian mode. All right, so I'm going to do one here where I have a TI-84 emulator here on the screen, and I want to evaluate that definite integral. Now, on the TI-84, what you would do is you would press the math key. Now, my menu looks a little bit different, but we still would go to number 9, FNINT, and it will pull up this kind of block scenario here, where you just have to fill in the block. So the lower limit of integration is 1. The upper limit of integration is going to be 3. And then we're going to type in our equation that we have, which is going to be x squared minus 2x plus 2. And words of wisdom, always put it inside of parentheses unless it like automatically puts parentheses there for you. And then the last block is going to be whatever your variables are. So this is how I type it in exactly the way it looks in my paper, and I press enter, and then it's going to give me my answer, which for this one is going to be 4 2/3, or 14 over 3. Okay, so we're going to do this next one using the TI Inspire in case you have one of those, and we'll kind of walk through it. And you see the buttons that you would have to press on the TI Inspire. For us to do a definite integral, we'd have to press this key, and then followed by selecting this option from the menu, and then we would start typing everything in. And so once I get everything typed in, we want to make sure that our calculator is in radian mode. So we're in radian mode, and then we're going to start filling in what it is we're trying to go from. Now I forgot we want to have 3 plus in front of it. And then we need to start filling in just like what we did before. So we wanted to have 2 times that integral. And we want to go from 0 to pi over 2. So we went from 0 to pi over 2, and then inside we're going to have tangent of x, and then we simply press enter. And we actually, it gives us infinity, which is an interesting concept, which we actually do not see. This is an improper integral where we're looking at evaluating the area up underneath the curve, and we actually have an asymptote for tangent at pi over 2. And it's something you don't learn about until later, but however, the process to typing it in, it still remains the same. All right, so now we're going to look at some properties of integrals. Now, since we defined our integral as a limit of a Riemann sum, since we're using limits for our definition, all of our limit properties can still come into play in terms of if we have a constant multiple, we could pull the constant outside of the limit, which in this case we'd pull outside of the integral. We could break up sum and differences into different parts. And so the same thing, so if I am adding or subtracting, I could break apart the limit just like I would do before. Notice how there is no multiplication property here. It's only, I can break up sum and differences and take out constant multiples. Now, another interesting thing is the order of integration. So if I had a definite integral defined to go from a to b of f of x dx, if I were to swap my bounds and go in the other direction, start with b and work my way back to a, it would be the same thing as what we had before, but it would just be negative. Now, there's also another property for the additivity. We saw that in an earlier video. So the overall area for the area up underneath the curve from a to c for some function of x dx is going to equal the sum of all the individual areas. Well, the way that would work from definite integrals, I would go from a to b, whatever the area is from a to b for f of x dx, plus the area from b to c for f of x dx to get the overall area from a to c. Right, let's use some properties of integrals here. So we're given the fact that the definite integral from 2 to 6 for f of x dx is equal to 10, and the definite integral from 2 to 6 for g of x dx is equal to negative 2. We want to find the following. So the first one, I want to find the value from 2 to 6 for f of x plus g of x dx. Well, in order to find its values, we're going to break apart the sum, and we're going to break it up to the area up underneath the f curve from 2 to 6 plus the area up underneath the g curve from 2 to 6. And now that we know we've broken it up in this part, we can substitute in. The first value is 10, the second value is negative 2, so the overall value for that would be equal to 8. Okay, let's look here at this second one. So the first thing that I noticed when trying to evaluate is I have that constant of 3 multiplying the g, so I could pull that outside of the integral. I could write this as 3 times the definite integral from 6 to 2 for g of x dx. Now, we know the value from 2 to 6 for g is negative 2, but we're going the other way around. So what I would have to do is I'd have to do a bound switch, which means that if I switch the bounds to go in the other direction from 2 to 6 for g of x dx, I would have to negate the integral that I was working with. And so now we would just take negative 3, multiply it to, in this case, the negative 2, and we would be able to get our answer. The answer to this would be positive 6. Okay, next one here. The value of the definite integral from 2 to 2 for g of x dx. Anytime your upper and lower limits of integration are the same constant, is always 0. And we think about that from a geometrical standpoint. This is our width. And so if I had a width of 0, no matter what my height is, 0 times the height is going to always be 0. And lastly, let's look at this piece here. So I'm redefining something here. So I am given that the value from 2 to 4 for f of x is going to equal 8. And I want to find the overall distance from 4 to 6. Well, in order to do that, in order to figure out what it is from 4 to 6, I look at what we have. We actually have the overall value from 2 to 6 for f of x dx to work with. And so the overall area, signed area from 2 to 6, is going to equal the signed area from 2 to 4 for f of x dx, plus the area that goes from 4 to 6 for f of x dx. And we're going to plug in values. So to go from 2 to 6 is 10. And I go from 4 to 2 is 8. And plus what we're looking for, which is from 4 to 6 for f of x dx. I would simply subtract the 8 over, and we would get 2.